The Pacific Ocean is hiding something, not at the surface where you could see it, underneath, in the dark, pressurized layers that satellites cannot photograph and weather apps cannot report. Down there, right now, a reservoir of heat so enormous that climate scientists are running out of polite language to describe it is building toward the surface. And when it arrives, it will not arrive quietly. Every major climate model on Earth is pointing at the same outcome, the same direction, faster than anyone predicted. Meanwhile, the sun won't calm down. Earth's magnetic shield is cracking in ways never seen before, and Phoenix hit 105 degrees in March. 3 systems, all escalating, simultaneously. Stay with me, because what the data actually shows is something nobody is talking about yet. Subscribe and follow along, because this story is not over. The same Pacific that is loading heat right now will keep sending signals, and those signals will keep arriving faster than the headlines can process them. When the spring barrier breaks and the models either confirm or collapse this forecast, this channel breaks it down in plain language before the noise takes over. You are going to want to be here for that. Now, let's get into it. Something changed in the models in March 2026, and the scientists who noticed it went very quiet. Not the kind of quiet that means nothing is happening. The kind of quiet that means too much is happening, and nobody is entirely sure what to say yet. Let me walk you through what actually shifted. The European Center for Medium-Range Weather Forecasts, the gold standard of global climate modeling, the system that major governments and militaries rely on for long-range planning, runs something called a seasonal ensemble forecast. Instead of one simulation of the future, scientists run dozens of slightly different versions simultaneously, tweaking the starting conditions each time, and then they watch where those simulations tend to cluster. It is, essentially, a voting system for the future. You are not asking one expert what they think. You are asking 60 of them at once and seeing which answer keeps coming up. In January 2026, the ensemble vote was unremarkable. The models projected a moderate El Niño forming sometime around the summer. Warm, but manageable. The kind of event that makes weather forecasters sit up a little straighter, but does not make them lose sleep. Then came February. The February model runs revised the projection upward to high-end moderate, possibly tipping into low-end strong. That is a meaningful jump in a single month. But scientists noted it, flagged it, and kept watching. By early March, the vote changed again, and this time, the shift was not subtle. The ECMWF ensemble began forecasting a strong to very strong event by late summer 2026. A handful of individual model members, the outliers, the ones that climatologists usually dismiss as statistical noise, entered what the community informally calls Super El Niño territory. Approximately 60% of all ensemble members are now pointing in the same direction. Strong, east-based, arriving fast. To understand why that matters, you need 2 reference points burned into the memory of modern climatology. The first is 1997 to 1998. The second is 2015 to 2016. These are not just historical footnotes. These are the events that climate scientists use as benchmarks the way engineers use stress test failures to understand exactly where a system breaks. The 1997 El Niño triggered catastrophic flooding across Peru and Ecuador, dried out Indonesia so severely that wildfire smoke blanketed the region for months, collapsed fisheries across the eastern Pacific, and contributed to the warmest global temperature on record at the time. The 2015 to 2016 event matched or exceeded it in several key metrics, pushed global average temperatures to a new record high in 2016, and left researchers genuinely shaken about how strong future events might become. Current model projections, as of early March 2026, are running ahead of where the 2015 event was at this exact stage of development. Read that again, slowly. ahead of 2015, at the same point in the calendar. Now here is where I want to be careful with you, because I am not here to terrify you with a forecast that might collapse. There is genuine scientific uncertainty baked into everything I'm about to tell you. These models could be wrong. There is a specific reason they could be wrong, and I will get to that shortly. But the central tension of this entire story is this. Either the models are dramatically overestimating what is forming in the Pacific right now, or we are watching, in real time, the earliest detectable stages of one of the strongest El Niño events ever recorded on Earth. There is no middle ground that fully resolves the data. You are either watching a false alarm, or you are watching history. The thing is, the real story is not happening at the surface. The most important signal right now is invisible from space, invisible from a weather satellite, invisible unless you know exactly where to look. And what scientists are seeing when they look there is, frankly, startling. The surface of the equatorial Pacific tells one story right now, but the ocean beneath it is telling a completely different one. Here is something that surprises most people when they first learn it. When scientists monitor El Niño, they do not just measure what the ocean looks like on top. They measure temperature anomalies down to several hundred meters. The subsurface, the thermal layers that sit invisible beneath the ocean's skin, carrying heat that has not yet reached the atmosphere, not yet affected a single weather system, not yet shown up in a single satellite image of sea surface temperatures. This subsurface data is, in many ways, the most honest signal available. It tells you not what the ocean is doing right now, but what it is preparing to do. And what it is preparing to do is, depending on your perspective, either fascinating or deeply concerning. Current observations show a massive pool of anomalously warm water sitting between 50 and 120 meters below the surface, stretching across the equatorial Pacific from the western warm pool near Indonesia all the way toward the coast of South America. Over the last 2 months, the volume of this warm, subsurface reservoir has expanded dramatically. Meteorologists have a phrase for this kind of subsurface heat. They call it the jet fuel for El Niño. That is not a metaphor I invented. That is the actual language used in briefing documents. Because that is essentially what it is: stored energy, waiting for the right trigger to release it toward the surface. The mechanism that releases it has a name that sounds deceptively gentle for something capable of reshaping planetary weather. It is called a Kelvin wave, not a surface wave in the sense you picture when you imagine the ocean. A Kelvin wave is an enormous subsurface pulse of warm water, sometimes hundreds of meters thick and thousands of kilometers wide, that travels eastward along the equator at its own slow, relentless pace. These waves are triggered by something called westerly wind bursts, temporary reversals of the normal Pacific trade winds that push warm water in the wrong direction. When those bursts occur, they compress the surface layer and send a thermal shock wave moving east, below the surface, towards South America. When it arrives, it pushes warm water upward. It forces subsurface heat toward the surface. And when enough of those waves arrive in sequence, the warm water erupts into the eastern Pacific like a pressure valve finally releasing, and El Niño conditions ignite. Here's what history tells us about this process. Before the monster El Niño of 1997, scientists observed an unusual buildup of subsurface warm water in the months leading up to the event. Same thing before 2015. The heat arrived underground before it arrived on the surface. The atmosphere had no idea what was coming until it was already there. What we are observing in early 2026 appears consistent with that pre-event signature, except the subsurface warm water anomaly right now is, by some measurements, larger in volume than those previous pre-event observations. Think about that as a concept for a moment. The fuel tank for what could become one of the strongest El Niños ever recorded appears to already be full, and the surface temperature readings, the numbers most people look at, have not yet fully reflected what is sitting directly underneath them. The surface looks moderate, but the subsurface looks like something altogether different. And if you want to understand why that gap matters, you have to zoom out even further, because the Pacific Ocean as a whole is not behaving the way it should be. The Pacific Ocean has been acting strangely for longer than most people realize, and the El Niño forming right now is not emerging from a neutral ocean. It is emerging from one that is already running hot. Since mid-2023, global sea surface temperatures have remained at or near all-time records for an extended, continuous period that has no clear precedent in the instrumental record. This is not a peak followed by a return to baseline. This is a prolonged elevation, month after month, that has persisted through what should have been a cooling La Niña phase. Even during the La Niña conditions of late 2024 and early 2025, the global ocean surface remained abnormally warm compared to historical averages. The baseline itself has shifted. The ocean you are launching this El Niño into is not the same ocean that hosted the 1997 event. The Northeast Pacific has been particularly unusual. A broad marine heat wave has been running along the entire western coast of North America, pushing sea surface temperatures well above normal from the Bering Sea all the way down to Baja California. These warm coastal waters are not just an environmental concern for marine ecosystems, though they absolutely are that. They also weaken the coastal cooling influence that normally moderates temperatures over land, and they interfere with the pressure gradients that organize storm tracks and weather patterns over the western United States. This helps explain, at least partially, some of the deeply strange weather that the western US has been experiencing throughout this winter and early spring. Now, layer onto that two longer-term ocean cycles that climatologists watch carefully when they are trying to understand how El Niño might behave. The first is the Pacific Decadal Oscillation, or PDO. This is a slow, decades-long pattern of ocean temperature variation across the North Pacific that shifts between warm and cool phases on timescales of 20 to 30 years. When the PDO is in a warm phase, it tends to amplify the atmospheric effects of El Niño events, shifting the jet stream more aggressively and producing more extreme weather patterns. The second cycle is the Pacific Meridional Mode, which describes how tropical Pacific sea surface temperatures respond to changes in trade wind strength. Under the right conditions, a warm Pacific Meridional Mode can accelerate El Niño development significantly. Scientists are watching both of these cycles right now because current ocean conditions appear to place both in configurations that could amplify the atmospheric response to whatever El Niño develops. This is the part that makes some researchers genuinely uncomfortable when they speak off the record. A strong El Niño launched from an already hot ocean during a warm PDO phase under supportive Pacific Meridional Mode conditions does not necessarily behave like a strong El Niño of the past. The historical playbook may not fully apply. The real-world impacts, the floods, the droughts, the temperature records, the disrupted monsoons, could be larger than past events of equivalent technical strength would suggest. In other words, even if this event tops out at strong rather than super El Niño status, it might hit the world harder than any previous strong El Niño, simply because the ocean it is embedded in is warmer than it has ever been during the satellite era. But here is the uncomfortable truth that every honest climate scientist will tell you, and it is the one thing standing between a confident forecast and a qualified one. There is a window right now where the forecast could fall apart entirely, and it has a name. Every year, between roughly March and May, El Niño forecasting enters a zone where the models become significantly less reliable. Scientists have a name for it. They call it the spring predictability barrier, and it is one of the more humbling features of modern climate science. A reminder that even the most sophisticated modeling systems on Earth still answer to the ocean. During these months, the Pacific climate system undergoes a seasonal reorganization. The coupling between the ocean surface and the atmosphere weakens. The signals that models use to project future El Niño strength become noisier and harder to interpret. Small atmospheric disturbances, a stray wind burst here, a temporary pressure shift there, can knock a developing event off its trajectory entirely. You can have all the right subsurface conditions in place and still watch the event fail to materialize, because the atmosphere simply did not cooperate during the window when it needed to. The most painful example of this in recent memory is 2014. In early 2014, seasonal model forecasts were screaming. Major El Niño, potentially historic. The subsurface heat was present. Kelvin waves were propagating east. Multiple models were in agreement. Climate scientists were writing briefing papers. News organizations were preparing coverage. And then the atmosphere just didn't follow through. The expected westerly wind bursts that should have locked in the event sputtered out. The surface warming in the eastern Pacific stalled. The event that everyone expected to be one of the strongest on record ended up being weak to moderate, barely enough to register in the official ENSO classifications. It became, in the climate science community, a cautionary tale about over-forecasting past the spring barrier. So why are researchers treating the 2026 situation differently, rather than simply repeating, "Remember 2014, and going back to their spreadsheets? The difference comes down to the subsurface. In 2014, the warm water reservoir, while present, was not as extensive or as deep as what is being measured right now. The volume of anomalously warm water in the Pacific subsurface in early 2026 appears to be substantially larger than the pre-event signatures observed before either 2014 or 2015. That is not a guarantee of success. The spring barrier does not care about volume metrics, but it does suggest that even if the atmosphere pulls back partially, there is more thermal energy available to sustain development than there was the last time a forecast of this magnitude was constructed. Multiple independent modeling systems are also now trending in the same direction. The ECMWF, the American CFS model. Several other operational systems. Model agreement at long lead times across independent architectures and data inputs is unusual enough that forecasters notice it. It does not eliminate uncertainty. Nothing eliminates uncertainty past the spring barrier, but the convergence of signals, the subsurface heat, the atmospheric preconditioning, the multi-model agreement paints a picture that is difficult to dismiss as noise. So here is where we actually stand. The forecast could still collapse like 2014. The spring barrier could scramble the signal and leave the models looking embarrassed by June. Or, and this is the scenario that a growing number of scientists are increasingly unwilling to rule out, we could be in the early observable stages of an El Niño event that has no real modern comparison. And while that question hangs unanswered over the Pacific, something unusual is already happening with global weather that does not need a forecast to explain it. It is already here, right now, in the temperature readings of cities that should still be weeks away from summer. Phoenix, Arizona recorded forecast temperatures approaching 105 degrees Fahrenheit in March 2026. Las Vegas was approaching 100 degrees. Los Angeles was nudging toward 100 degrees as well. Sit with that for a moment. Not because extreme heat is new to those cities. It is not, but because of when it is occurring. March, not June, not July. Not the height of summer when the jet stream has retreated north, and the desert cities have already settled into their brutal seasonal rhythm. March, when, by historical standards, Phoenix should be sitting in the low to mid-70s, when Las Vegas should feel like a pleasant spring afternoon. These temperatures would not just break March records, they would shatter them by several degrees, and the mechanism responsible for producing them is not a freak anomaly. It is a pattern that researchers have been watching develop with increasing concern. The technical term for what created this event is diabatic ridge building, a phrase that sounds dry and academic until you understand what it describes. A climate scientist named Daniel Swain, who has become something of a go-to voice for extreme weather communication on the West Coast, laid out the mechanism clearly. In this process, heavy precipitation somewhere upstream, in this case, a storm system over another part of the country, causes large amounts of air to rise rapidly. As that air rises, the water within it condenses, and that condensation releases heat directly into the upper atmosphere. That injected heat then strengthens a nearby high-pressure system, sometimes dramatically and over a short period. The high-pressure system, what you might have heard referred to as a heat dome, creates an area of the atmosphere where air descends rather than rises. And here is the part that matters for the temperature readings. When air descends, it compresses. When it compresses, it warms rapidly. The air temperature at the surface under a strong descending ridge can climb to levels that feel physically wrong for the time of year, because in a mechanical sense, the atmosphere is squeezing energy into a region that is not equipped to release it. You have heard of this process before, even if you did not know its name. This is the same mechanism, operating in the same general region, that produced the Pacific Northwest Heat Dome event of June 2021, an event that killed hundreds of people in Canada and the northwestern United States, shattered all-time temperature records in cities like Portland and Seattle, and forced climate scientists to revise their estimates of how extreme heat events in that part of the world could actually get. Lytton, British Columbia, recorded 49.6 degrees Celsius on June 29th of that year, a temperature that was not merely unprecedented for Canada. It was a temperature that the country's prior climate models suggested should have been essentially impossible. That event happened in late June. The pattern driving the current western U.S. heat anomaly is producing comparable atmospheric ridge strength in early March, which means the same basic physics that scrambled our understanding of summer heat extremes is now operating nearly 4 months earlier in the calendar year. The atmosphere is not warming uniformly. It is reorganizing. And the reorganization is producing extremes in places and at times that our historical expectations were simply not built to accommodate. But the heat wave itself is only part of the story, because the winter that preceded it was not a normal winter either. And to understand what the atmosphere is actually telling us, you need to look at what has been happening in the Pacific's circulatory system long before any of these headlines were written. The atmosphere over the Pacific may be changing shape right now in ways that predate the actual arrival of El Niño, and that is, depending on how you interpret it, either reassuring or significantly more alarming. To understand what is happening, you need a mental picture of something called the Walker circulation. Under normal Pacific conditions, meaning the baseline state that climate science has used as its reference for the past century, trade winds blow westward across the equatorial Pacific, pushing warm surface water toward Indonesia and the western Pacific. Near Indonesia and the Philippines, that warm surface water heats the air above it, causing it to rise. Rising air creates clouds, rainfall, thunderstorms, and a large area of low pressure at the surface. That air then travels eastward at high altitude, cools over the central and eastern Pacific, sinks back toward the surface, and the whole system loops back around. This is the Walker circulation, a massive atmospheric conveyor belt driven by the temperature difference between the warm western Pacific and the cooler eastern Pacific. It is one of the fundamental organizing structures of tropical weather on Earth. El Niño disrupts it. When the eastern Pacific warms, the temperature gradient that drives the Walker circulation weakens. Trade winds relax. Warm water sloshes back eastward. Rainfall patterns shift dramatically. The rising air that normally sits over Indonesia migrates toward the central Pacific. The sinking air that normally suppresses weather over Peru and Ecuador weakens, allowing flooding rains to develop. The whole system tilts. What is interesting about the current observations is that this tilting may already be underway, before the surface temperatures of the eastern Pacific have fully committed to El Niño conditions. Current atmospheric data shows weakening trade winds across parts of the equatorial Pacific. Upper-level wind measurements show anomalous easterly flows at high altitude that are consistent with early El Niño atmospheric coupling. Sea level pressure anomalies are running below normal across large portions of the Pacific, which encourages the development of thunderstorm systems that further weaken the Walker circulation. Convection, the meteorological term for large-scale rising air and associated storms, has increased noticeably in the Central Pacific in ways that reinforce the weakening of normal circulation. In plain language, the atmosphere over the Pacific appears to be preconditioning itself for El Niño before the surface ocean warming that formally triggers it has fully arrived. The ocean and atmosphere are beginning to talk to each other in the language of El Niño. And once that conversation begins, it tends to be self-reinforcing. Warmer ocean weakens the trade winds. Weaker trade winds allow the ocean to warm further. The two systems feed each other in a loop that historically has been very difficult to interrupt once it achieves a certain momentum. The question of what that loop produces at its maximum and where on Earth it sends the consequences is not academic. It is the difference between a difficult year for global agriculture, water supply, and disaster preparedness, and something that forces a fundamental reassessment of what the climate system is capable of. When a strong El Niño event matures and its warmth spreads across the equatorial Pacific, it does not just change local weather off the coast of Peru. It reorganizes the atmospheric circulation of the entire planet, not nudges it, not adjusts it slightly at the margins, reorganizes it. And it does so across timescales of months, in patterns that affect agriculture, water supply, public health, and disaster preparedness on every inhabited continent. The impacts follow well-documented historical patterns, not perfectly predictable, not identical from one event to the next, but consistent enough that scientists can construct reasonable probabilistic forecasts for regions that sit thousands of miles from the nearest point of the Pacific Ocean. Think about that for a moment. A temperature anomaly in the eastern equatorial Pacific, a patch of ocean that most people on Earth will never see, reshapes the weather experienced by billions of people who have no idea it exists. That is how tightly coupled the planet's climate system actually is. Pull one thread, and the entire fabric shifts. The Pacific jet stream is the first thread to move. This high-altitude river of fast-moving air, which sits roughly 8 to 12 kilometers above the surface and steers weather systems across North America the way a track directs a train, strengthens and shifts southward under El Niño forcing. That shift sounds technical and abstract until you translate it into ground-level consequences. The southern tier of the United States, the Gulf Coast states, the Southwest Desert, Florida and California, tends to receive significantly more precipitation during El Niño winters. Storm tracks that would normally be deflected northward get pushed south, delivering repeated rounds of heavy rain and, in some cases, catastrophic flooding to regions that spend the rest of their time in serious drought. California's most significant wet years in recent memory have clustered around moderate to strong El Niño events, which is one reason water managers and reservoir operators watch ENSO forecasts with the kind of attention most people reserve for their bank accounts. The flip side of that same jet stream shift plays out across the northern United States and southern Canada, where El Niño winters tend to run warmer and drier than normal. Reduced snowpack in the mountain ranges that feed major river systems translates directly into elevated wildfire risk the following summer, and into water shortages the following year, and into agricultural stress the year after that. The downstream consequences of a single ocean temperature anomaly can ripple forward through a regional economy for years. In the tropics, the changes tend to be more dramatic and more immediate than anything experienced at higher latitudes. El Niño suppresses Atlantic hurricane formation through a mechanism that is almost elegant in its brutality. The strengthened upper-level winds associated with El Niño increase what meteorologists call wind shear, the change in wind speed and direction with increasing altitude. Developing tropical cyclones are extraordinarily sensitive to wind shear. A strong enough shear environment essentially tears a forming hurricane apart before it can organize into a coherent circulation. For Atlantic hurricane seasons that overlap with a strong El Niño, this suppression is, from a purely damage minimization standpoint, a rare piece of good news in an otherwise complicated story. The Eastern Pacific runs in the opposite direction entirely. El Niño conditions favor increased tropical cyclone development in the Eastern Pacific Basin, producing more storms and stronger ones in a region that threatens Mexico's Pacific coast. The same event that quiets the Gulf of Mexico can simultaneously energize the ocean west of Acapulco. Southeast Asia and Indonesia receive some of the most severe impacts of any region during a strong El Niño. The convective rainfall that normally anchors over the Western Pacific, the thunderstorm systems that sustain the monsoons of the Philippines, Indonesia, Malaysia, and parts of mainland Southeast Asia, migrates eastward when El Niño displaces the warm surface water that drives it. What remains behind is anomalous dryness, sometimes severe dryness, sometimes catastrophic dryness. During the 1997 to 1998 El Niño, the resulting droughts across Indonesia were so prolonged and so extreme that wildfires burned across vast areas of Borneo and Sumatra for months. The smoke those fires produced did not stay local. It blanketed the entire region in a thick haze that persisted for weeks, closed airports, grounded aircraft, triggered respiratory health emergencies across multiple countries, and ultimately caused economic losses that took years to fully tabulate. Thousands of kilometers to the south, Australia's monsoon weakens under strong El Niño forcing. The wet season rainfall that replenishes reservoirs, sustains agriculture, and maintains river systems across the continent's tropical north can be reduced dramatically. Farmers in Queensland and the Northern Territory have learned to watch Pacific sea surface temperature anomalies the way other people watch stock markets, because the connection between what happens in the equatorial Pacific and what falls from the sky over their fields is, historically, one of the strongest statistical relationships in global climate science. Western South America experiences the most direct impact of any region because it sits closest to the source. The warm water that builds in the Eastern Pacific drives intense atmospheric convection off the coast of Peru and Ecuador, producing rainfall events of a magnitude that the normally arid coastal zones of those countries are structurally unprepared to absorb. During the strongest historical events, rivers that locals sometimes describe as seasonal trickles have flooded to levels that permanently altered the physical layout of human settlements. Communities that had existed in the same location for generations were simply erased. Agricultural systems built around the expectation of dry conditions were overwhelmed by water. They had no drainage infrastructure to manage. The fisheries that anchor the Peruvian economy collapse during major El Niño events as the warm surface water suppresses the cold upwelling from depth that supports the marine food chain. The anchoveta fishery, one of the largest by volume in the world, has historically seen near-total shutdowns during strong events, a collapse that reverberates through global fish meal markets and into livestock feed prices across multiple continents. Now, here is the number that transforms everything described above from serious to potentially unprecedented in the context of 2026. Following the 2015 to 2016 El Niño, 2016 became the warmest year in the global instrumental temperature record at the time it occurred. The mechanism is straightforward. When El Niño releases its accumulated oceanic heat into the atmosphere, it does so at a scale so enormous that the effect shows up in global average temperature measurements. It produces a measurable, significant spike layered directly on top of the long-term background warming trend. In 2015 and 2016, the combination of those two signals, the El Niño heat release and the underlying trend, was sufficient to break global temperature records that had stood for decades. Records that scientists had not expected to fall for years fell within a single 12-month period. In 2026, the background ocean temperature is already significantly higher than it was before 2015. This is not a marginal difference. Global sea surface temperatures have been running at or near record levels continuously since mid-2023, through what should have been a cooling La Niña phase, and into the present. The thermal baseline has shifted upward in a way that is measurable, documented, and not fully explained by any single factor. If a strong El Niño now adds its characteristic atmospheric heat release on top of a global ocean that is already running warmer than it was before any previous strong El Niño on record, the global temperature record set in 2016 may not survive the following 12 months. The dominoes are not standing in isolation. They are not waiting to be pushed. They are already leaning, and the force that could topple them is still building beneath the surface of the Pacific. The question that genuinely deserves to be asked, the one that climate scientists are beginning to raise in language that is more careful and more measured than usual, in the kind of careful language that scientists use when they are not yet certain how alarming to be, is not simply how strong this El Niño might become. It is a more fundamental question than that. It is what happens when a potentially historic El Niño develops inside a climate system that is no longer the same system it was the last time we measured something this large. The tools we use to forecast it were built on historical data. The benchmarks we compare it to occurred in a cooler ocean. The projections we make about its impacts are based on events that unfolded in atmospheric and oceanic conditions that may no longer exist in the same form. We are, in a very real sense, attempting to use an old map to navigate a landscape that has quietly changed around us. And here's the thread that makes this entire story stranger than it already is. While the Pacific has been patiently loading what could be its most powerful event in the modern observational record, something else entirely has been changing overhead. Quietly, invisibly, in the architecture of the magnetic field that surrounds this planet, in ways that nobody has yet formally connected to this conversation. But that connection, if it exists, changes the nature of the question entirely. You have been watching one story this entire time, and it looks like a weather forecast. It has the shape of a weather forecast. It uses the language of weather forecasting. Ensemble models, sea surface anomalies, subsurface heat reservoirs, spring predictability barriers. But step back far enough. Look at the full picture rather than any individual piece of it, and it becomes something else entirely. It becomes a story about a system that is operating outside the boundaries of its own historical record. And that is a different kind of story. The Pacific Ocean is accumulating subsurface heat at a rate that has forecasters reaching for comparisons to the months before 1997. The event that reshaped global weather patterns, collapsed fisheries, triggered catastrophic flooding across 3 continents, and became the reference point that climate scientists have spent nearly 3 decades measuring everything else against. The atmospheric circulation that governs global weather is already showing pre-El Niño signatures before the event has formally arrived at the surface. The broader ocean system that El Niño is embedded in, the global ocean, not just the Pacific, is running warmer than at any comparable point in the entire satellite record. A major western United States heat wave in March, not July, not August, not the peak of summer, but March, has already demonstrated that the atmosphere is capable of delivering extreme heat events completely outside the expected seasonal window, and multiple independent climate models, built on different architectures, fed by different data streams, run by different institutions in different countries, are converging on the same forecast. Strong to very strong. At a lead time when that kind of multi-model convergence is historically unusual enough to make veteran forecasters pause and look twice. These are not separate stories happening to share a news cycle. They are facets of the same story. Different angles on the same object. And the object is not simply a bad El Niño that might be coming. The object is the realization that the system which produces El Niño, the coupled ocean-atmosphere engine of the Pacific, the mechanism that has been cycling through warm and cold phases for as long as the ocean has existed, is currently operating in conditions that have no direct historical precedent in the era of modern climate monitoring. No precedent in the satellite record. No precedent in the instrumental temperature record. We are watching a familiar process unfold inside an unfamiliar container, and our forecasting tools were not built for the container we are currently working with. The events we use as benchmarks were measured in a different ocean. 1997 occurred in a Pacific that was cooler than the one we have now. 2015 occurred in a Pacific that was cooler than the one we have now. The historical playbook for what a strong El Niño does, how it affects rainfall in Peru, drought in Indonesia, wildfire risk in Australia, storm tracks across North America, was written based on observations made in ocean conditions that no longer fully apply. We are attempting to use a manual written for one machine to operate a different machine that superficially resembles it. Most of the instructions probably still hold, but the places where they do not hold are exactly the places where the consequences are largest. The spring predictability barrier still exists and still carries genuine uncertainty. I want to be clear about that, because this channel does not trade in false certainty, and the barrier is real. Between March and May, Pacific climate forecasting becomes significantly less reliable. Small atmospheric disturbances can redirect a developing event. The ocean-atmosphere coupling weakens seasonally. The signal gets harder to read. Everything I have described in this video, the subsurface heat, the atmospheric preconditioning, the model agreement, could theoretically still unravel. The forecast could still collapse the way the 2014 forecast collapsed, quietly and without ceremony, leaving the models looking dramatically overconfident by summer. But here's the thing about uncertainty that I think gets lost in the way science communicators typically handle it. There is a temptation, a very understandable one, to frame uncertainty as a reason for reassurance. To say the models might be wrong, and let the audience interpret that as probably fine. To present the spring barrier as an escape hatch, as evidence that the alarming forecast might not materialize, and therefore that the appropriate response is to wait and see. And in terms of strict probabilistic language, that framing is technically defensible. Nobody knows yet whether 2026 becomes the strongest El Niño in the modern record, or whether the forecast falls apart by June. That is genuinely true. But uncertainty is not the same as safety. This is a point worth sitting with for a moment. Uncertainty does not mean the dangerous outcome is unlikely. It means the distribution of outcomes is wide, and when you are operating in a system that is already running at record temperatures, with pre-existing subsurface heat that exceeds the pre-event signatures of any previous strong El Niño, a wide distribution of outcomes is not comforting. It is alarming. Because a wide distribution in a hot system means the upper end of the range, the tail risk, the scenario that sits at the extreme edge of what the models are showing, is not a fringe possibility to be briefly acknowledged and then set aside. It is a scenario that deserves serious, sustained attention in a way that goes well beyond a seasonal weather briefing. The subsurface fuel tank is full. That is not a model projection. That is a current observation measured right now in the water. The atmosphere is already beginning to respond to the ocean heat building beneath it, showing the early signatures of Walker circulation weakening and trade wind relaxation that historically precede a developing event. The ocean baseline is the warmest it has been during any El Niño development period in the recorded history of this measurement. And the March temperature readings in Phoenix and Las Vegas, 105 degrees and approaching 100 degrees respectively, in the first week of spring, are, in a very real and somewhat uncomfortable sense, likely to be the mildest thing this story produces before it concludes. What comes next is not written yet. The spring barrier will either scatter this forecast or confirm it. By June or July, the ambiguity that currently surrounds the 2026 El Niño outlook will have resolved into something much clearer in one direction or the other. Either the event strengthens, as the models suggest, and we begin the process of real-time impact forecasting for every affected region on Earth, or the atmospheric coupling fails to lock in, and the subsurface heat dissipates without fully reaching the surface, and the forecast joins 2014 in the file of cautionary tales about overreading early signals. One of those outcomes will happen. We will know which one before summer ends. But right now, in this moment, in the data that is available today, in the model outputs, in the subsurface thermal profiles, in the atmospheric pressure anomalies, in the weakening trade wind measurements, in the sea surface temperature trends along the coast of South America, there is something building. Something that does not respond to the calendar, or to the news cycle, or to the question of whether it is convenient timing. Something patient in the way that oceans are patient, moving on timescales that make human planning horizons feel brief and inadequate. Something enormous in the way that only planetary scale systems can be enormous. Something that the smartest climate models on Earth, run by the most experienced teams in the field, are beginning, with characteristic scientific caution, to describe using words they do not reach for in ordinary forecast cycles. And if those models are reading the signal correctly, not all of them, not even the majority of the most extreme members, but if the ensemble as a whole is pointing in the right direction, then what is forming beneath the surface of the Pacific right now is not simply a forecast. It is a reckoning. A slow, pressurized, thermodynamically inevitable release of energy that has been accumulating for years, preparing to reorganize the atmospheric circulation of a planet that is already running hotter than it was the last time something like this happened. The ocean loads its gun slowly. It always has. It loaded it before 1997. It loaded it before 2015. It is loading it now in the dark water below the surface, hundreds of meters down, where no satellite can photograph it and no weather app can report it. It has been loading this particular one for a long time. And the question the data raises, the question it raises very clearly, even if it cannot yet fully answer it, is not whether it will fire. The question is what the world looks like when it does. Inside a climate system that has never been this warm the last time it happened, alongside a sun that refuses to quiet down past its predicted peak, and beneath a magnetic shield that is developing structural weaknesses that have no precedent in the satellite era. 3 systems, all escalating, simultaneously. And the question that climate science has not yet formally asked, the one that connects all 3, may be the most important question of this entire story.